According to string theory, strings are one-dimensional but vibrate in all other dimensions. This string, however, is not the same string that is used for flying kites. That string is between 10 to the 32 and 10 to the 33 times larger. Planck length. The Planck length is a unit of length. There is also Planck time, which the amount of time it takes light to travel one Planck length in a vacuum. It's actually zero. We have a quantum foam. According to the space-time theory, quantum foam, which is also known as space-time foam, is the foundation of the fabric of the universe. It is impossible to directly observe or measure this because it's so small. Top quark. 1 octometer. The top quark is the smallest quark, which means it's the most massive. It's almost 100,000 times as massive as the up quark, which is the lightest of the quarks. The top quark's mass is 173 billion electron volts. Neutrino, 1 octometer. Neutrinos pass through ordinary matter like you and me all the time. In fact, they're doing it right now. Neutrinos have no charge, so they are only affected by the gravity and the weak force. However, they are so small that they are barely affected. Bottom quark, 300 octometers. The bottom quark is also called the beauty quark because it's for some reason flawlessly beautiful. It is third generation and quickly decays into up and charm quarks. Charm quark, 1 zeptometer. The charm quark and strange quark are second generation of matter. They will quickly decay into up and down quarks, which are the first generation of matter. The charm quark, for some reason, is charming. Strange quark, 4 zeptometers. Strange quarks are very strange. They are 50 times as massive as the up quarks, but are smaller. Isn't that strange? Very much so. Strange matter is made up of up, down, and strange quarks. Down quark, 8 zeptometers. There are 6 flavors of quarks. They are up, down, strange, charm, top, and bottom. The smaller the quark is, the more mass it has. As a result, the up and down quarks are actually the lightest of the quarks. This down has a charge of negative 1/3. Up quark, 10 zeptometers. There are 6 flavors of quarks. They're up, down, strange, charm, top, and bottom. The smaller quark is, the more mass it has. As a result, the up and down quarks are actually the lightest of the quarks. This up quark has a charge of plus 2/3. High energy neutrino, 15 zeptometers. Neutrinos of higher energy are larger. For more about neutrinos, go to neutrino, which shows the average size. It's a whopping 15,000 times smaller. Range of the weak force, 10 atometers. The weak force is one of the 4 fundamental forces of nature and is the weaker of the 2 nuclear forces. As distance increases, its strength decreases at just 10 atometers. The weak force is so weak it is unmeasurable. Lengths shorter than this are not confirmed. 100 atometers. All of the objects smaller than this are unmeasured. The sizes they appear are only estimates. Some things, like quantum foam, aren't hypothesized, they aren't fact. And some of the sizes that we just saw are just simply made up. Neutron, 1 femtometer. Neutrons are found within an atom's nucleus. They're thousands of times smaller than the atom itself. They have 2 down quarks and 1 up quark. Therefore, the neutron's charge is minus 1/3 minus 1/3 plus 2/3 equals 0. Proton, 1.75 femtometers. Protons are found within an atom's nucleus. They are thousands of times smaller than the atom itself. They have 2 up quarks and 1 down quark. Therefore, the proton's charge is plus 2/3 plus 2/3 minus 1/3 equals plus 1. Electron, classical. Electrons are so small that their size can't be accurately measured. The size of an electron varies greatly depending on how it's measured, whether it's based on the quantum model or, in this case, the classical model. Chlorine nucleus, 6 femtometers. A chlorine nucleus has 17 protons and anywhere from 11 to 34 neutrons. However, the majority of these isotopes will decay within minutes, if not seconds. The only stable isotopes, isotopes are chlorine 35, 18 neutrons, and chlorine 37, 20 neutrons. Even numbers of neutrons, especially magic numbers, tend to be more stable than an odd ones. Helium nucleus, 3 femtometers. The helium nucleus is 1,000 times smaller than the atom, like a marble in a football field. The only reason matter feels solid is because atoms repel. If atoms didn't repel, everything would fall through each other. Uranium nucleus, 12 femtometers. Uranium is the heaviest natural element. It also has the largest nucleus of all the natural elements. Uranium-238, the most common isotope of uranium, has a half-life of 4.5 billion years, approximately the time the Earth existed. Gamma ray wavelength, 1 picometer. Gamma rays have a very high frequency. They can come from radioactive decay. Oh, and by the way, it's not actually light blue as it appears to the left. Helium atom, 25 picometers. Hydrogen atoms are larger than helium atoms because more protons in an atom's nucleus pull the electrons closer. However, additional shells increase the size of the atoms. Cesium, the largest atom, has the most shells with the fewest electrons. The potential winner is francium. However, it has not been measured. The smallest thing visible to an electron microscope, 50 picometers. Electron microscopes allow us to see very small things like atoms that would otherwise be invisible because they are smaller than the wavelength of visible light. Angstrom, 100 picometers. An angstrom, which is named after Swedish physicist Anders Jonas Angstrom, is 1/10 of a nanometer. The symbol used for an angstrom is A. With a ring. The angstrom is used to express the size of atoms or transistors. Hydrogen atom, 110 picometers. Hydrogen is the most abundant element in the universe. It's usually just a proton and an electron. Hydrogen atom is so small that you can't even see it with your naked eye, even if you try your hardest. Carbon atom, 160 picometers. Carbon is the basis of all life on Earth. This is because carbon atoms can create 4 covalent bonds, which means it can bond in thousands of ways with oxygen, nitrogen, hydrogen, carbon, and other elements. Cesium atom, 500 picometers. Atom size is measured by the distance of the nuclei in the covalent bonds. The shells don't actually look like this. The cesium is the largest atom, but its atomic number is not the highest, at only 55. Why? Well, you saw helium, see helium atom. Water molecule, 280 picometers. I like to think that whenever I drink water, I drink Mickey Mouse heads. That's because it's actually shaped like the Mickey Mouse head. Do you too? Oh, you don't? Well, you should. Carbon nanotube, 1 nanometer. Carbon nanotubes are the strongest material yet discovered. As another bonus, they're lightweight. As a result, nanotubes have a lot of potential applications, including buildings, batteries, solar panels, and possibly even a space elevator. Buckyball, 1 nanometer. Buckyballs, which are also called Buckminster fullerenes, are made of 60 carbon atoms. The shape it forms is a truncated icosahedron, which is also the shape of a soccer ball. Soccer balls are not perfectly spheres. A solution made completely out of buckyballs is violet. Glucose molecule, 800 picometers. Glucose is a simple sugar. Plants make glucose through photosynthesis and turn it into complex sugars. When we as humans eat plants or animals that have eaten plants, we eat complex sugars which we break down into glucose again, which we use for energy. X-ray wavelength, 500 picometers. Although X-rays do not have the highest frequency, it is still a bad idea to bask in them. Don't do it! Usually, you should have a lead shield. The thicker the lead is, the more protection. However, a few X-rays will always get through. The thicker lead just lowers this chance, but doesn't eradicate it completely. Phospholipid, 2.5 nanometers. Phospholipids are beautifully amazing little molecules. You have millions of them in your body. Phospholipids are actually a special type of lipid that make up cell membranes. Transistor gate, 5 nanometers. Transistors in computers are continuing to get smaller. In 1971, they were 400 times larger at 10 micrometers. Now we are down to 5 nanometers, but in the future they might get even smaller. How small will they get? Moore's law predicts we can make new transistors half as big as before every 2 years, but definitely not to the size of an atom. Alpha helix, 1.2 nanometers. The alpha helix is one of the secondary structures of proteins. Many proteins have alpha helices within them. Hemoglobin and myoglobin are proteins that are made of about 70% alpha helices. Phospholipid bilayer, 5 nanometers. Cell membranes are made of phospholipid bilayers. They can form naturally because the heads attract to the water and the tails repel from the water. As a result, tails come together, forming the bilayer. Porcine circovirus, 17 nanometers. The porcine circovirus is one of the smallest viruses. It requires only 3 proteins to replicate. If you consider viruses to be alive, then the porcine circovirus is the smallest living thing. However, scientists do disagree whether viruses are alive or not.